In this portion, we're going to talk about discuss how the results of U and Q are affected by the pressure gradient. So U is actually the velocity, if you remember the very first part that we're talking about, this one. Okay, and then the Q is the previous video we talked about it, about the flow rate Q. So how are they being affected by pressure gradient? So it's the same system that I described in the last lesson. Okay, a lot of videos ago. But I think it is not that strong. Okay, so I decided to actually do up a Excel sheet. Okay, so in order to let you visualize what the pressure gradient would look like. Okay, so I have the equation makes smaller. Okay, so where is it? Okay, so I have this thing. So this is actually the u, right? The velocity. While this is the flow rate. So we have four conditions. Okay, or maybe perhaps five lah, but I'll just let it four first. So when it is equals to 0, okay, when what is equals to 0? When the pressure gradient is equals to 0, there is no velocity field. Okay, so what does this mean? So when this dude is equals to 0, the whole equation becomes 0. That's why there's no velocity flowing, it's constant, it's stagnant, okay? So that's what it means. But if there is a negative partial p partial x, it's actually positive. Why is it positive? You're going to take a look in this equation. R at this point, okay, or maybe R at any point, okay, it's definitely smaller than the capital R, right? This capital R maybe some value 8. So maybe at this point R is equals to 1, but it's always smaller than the capital R. So if let's say this is 1 square minus 8 square, you have negative. So this is negative value. And then if this pressure gradient is also negative, so they cancel out, become positive. So this is why we have positive over here. Okay, so this is how exactly this whole thing works. So make sure don't be scammed or cheated by all this equation. This is definitely negative. Okay, so what I did was I drew out an equation. Okay, I drew out a Excel equation which is similar to that. 1 over 1 quarter. Okay, I assume that the dynamic viscosity is actually negligible, and then del p del x is actually this one, so I set it as 1. Okay, and then if I set it and then if I set this, okay, a1 is actually this 1 2 3 4 5 6, so it will be r, okay, this small r, and then this 20 square I'll keep it constant throughout. Okay, it is r square, so which is at the top over here. So if my pressure gradient is actually so called negative, okay, so what does this mean? In fact, this picture is actually wrong. Okay, now but anyway, the r and the r is still the same. Okay, the explanation is still the same, just that what I drew over here is wrong. So if let's say I have the negative pressure gradient, well, I also know that this will be negative for any case. Okay, why do I say so? Okay, because if r is going in this direction, if it's minus r, if you square it is still r square, right? You get what I mean? So if let's say this is 3, and if this is minus 3, if you square both of them, you will still get 9, right? You get what I mean? So this is why it is lah. Okay. So that's why when talking about pipe, we're only talking about only this one direction. You're talking about polar coordinates, only a magnitude and a degree and an angle lah. Okay. So this is what it means, and then I've say a lot of rubbish. So now let me show you. Okay. So this equation, okay, am I lagging? Hold on. So this thing shows 1 quarter. I mean, yeah, 1 over quarter. And then multiply by, assume that there's negative 1. Okay, I say that it is positive. Okay, if it's positive. I mean, sorry, I'm saying that if the pressure gradient is negative. Okay, so that's why I put negative 1 over here. So this is pressure gradient. And then this is actually this is actually this r square over here. And then this is actually r square, the capital R square. So this one will be throughout 20 square. Okay, As you can see, they are all 20 square. Okay, no matter how I click, but this small little r square will change along the distance. So what does this mean? Because I'm trying to plot out a graph to describe the path. Okay, let's say r is at this point, this is 1, r equals to 2, r equals to 3. So I plot it out and then I see how does the pressure gradient looks like. And therefore when I plot it out, okay, what you will see is this graph over here. So this is exactly the same. This is actually the flow of the pipe. Okay, so this means that it is actually going in this direction. It is actually the same direction as the one described in the. This is actually the velocity profile. Okay, surprisingly, this is actually the velocity profile. Okay, why do I say so? Okay, so if you were to take a look, okay, this equation over here is u, velocity. If you plot against certain values, along certain values, you'll get a velocity at this point. Eventually you plot everything, you get a velocity profile. And this velocity profile is dependable on the pressure gradient. Okay, whatever the pressure gradient is, you actually change the outcome. Okay, and then if the pressure gradient is negative, okay, because this portion over here will be negative, I already said. And then if this is so negative, so everything will be positive. This is why it's moving forward in this direction. Okay, so as the pressure gradient varies, okay, let's say the pressure gradient becomes smaller and smaller, meaning this value, okay, it's negative 40, and then later I put a negative 60, okay, getting smaller and smaller. Okay, although this value is big, but then it is going in the negative side, so it's getting smaller and smaller. So as this value is getting smaller and smaller, we can see that the pressure gradient is gonna be more steeper. Okay, what do I mean? Let's say if you're looking at this point, this is actually the pressure gradient for only when I sub in it is equals to -1, right? So what if I sub in -2, -3, -4? Okay, let's take a look. If I do that, and if I plot it out, okay, this blue line represents when the pressure gradient is 1. This red line represents this one. Okay, when pressure gradient is 2, and this is pressure gradient is 3, and pressure gradient is 4. So if your pressure gradient, okay, if it's getting smaller and smaller, okay, it's gonna be steeper and steeper. Okay, it's gonna be steeper and steeper along this one. So you gotta see a more steeper curve. Okay, and do take note that this is actually the velocity profile. Okay, don't be confused by the previous videos on talking about the pressure gradient. Pressure gradient, the graph is totally different graph. It's -2, meaning that's at first the pressure gradient at first the pressure over here is actually very high, and then it slowly decrease. Right, it slowly decrease up to this point is equals to 0. This is what it means. Okay. Let me repeat again, okay? So the pressure gradient, okay, let's say pressure gradient is over here. This is at the very edge of the pipe. Across partial x, meaning across this x direction, right? So if your x direction increases, okay, let's say because this one says that it's negative gradient, so it's gonna go down. So therefore, as x goes in this direction, okay, the pressure gradient gonna fall and fall and fall and fall up to this point and stops. Because this is the max velocity. If you know that pressure goes up, velocity means down, right? So similarly at this point, P is actually pressure is very low and then velocity is very high compared to this point. At this point, pressure is very high, velocity is very low. Okay, I hope I didn't confuse you anything, okay, so far. Okay, and so this is the velocity profile. So the flow rate will actually go in this direction. It's gonna go here, and if you were to if you were to decrease the pressure gradient, okay, much more decreasing, you can actually increase the flow rate as shown over here. Okay, it is governed by a different formula. Okay, so for example, this is equals to 0, right? If it's equals to 0 over here, so what is equals to 0? Okay, let me repeat again. for this case, what equals to 0 is actually the pressure gradient is equals to 0. In this case, pressure gradient is also equals to 0. So how does this pressure gradient affect our velocity and affect our flow rate? So therefore, in this case, if it's equals to 0, everything goes to 0. So no volume flow, no velocity flow, right? So if it's negative pressure gradient, as you can see, is a positive. So it's a velocity profile going in this direction, which is the normal one. But however, it's increasing now because the p itself has a variable. As you can see from my relationship, I have decreasing pressure gradient -2, and then -3, -4. As I decrease my pressure gradient, my velocity profile will be steeper, right? You see, even steeper. So as your pressure, as your pressure gradient decrease, you're gonna see this thing happening. Okay, so if your pressure gradient decrease in the flow rate, okay, how does it affect the flow rate? So as you know that this is a negative, so negative and negative gonna be positive. So the pressure will increase based on the flow rate will increase based on the pressure increase. Okay, because the pressure is like this partial differentiation is a constant. No, I mean it's a multiplier. Okay, it's gonna amplify how big this number is. This is always constant. However, when the pressure increase, you're gonna go when the numbers are okay. When the numbers gonna increase, you're gonna increase the number of volume flow rate into certain pipe. So we talked so much about the negative gradient and 0. So let's talk about what if it's positive 1. Okay, if the pressure gradient is positive 1, we know that this is going to be negative, right? This is going to be negative. Okay, so this is negative. Sorry, this is going to be negative. And then this is 1, right? So everything going to go the other way around. So therefore this is negative. So what will be the graph looks like? I also plotted out a relationship. So instead of -1, okay, in this case, in previous case of -1, right? This is the pressure gradient. Okay, I plot 1, and then 2, 3, and 4. As you can see, it's changing. Okay, it's only this thing changing only. As you can see, the pressure gradient is changing. So if you're going to take a look on that, what will you see? Okay, so it's going to be in totally another way around. Okay, instead of going in this direction, it's gonna go for this direction. So if you have the pipe, so if you take a look, is this graph, right? So if, let's say I plot over here, you can see, as you can see, I plot one of it. So you can see it's the velocity profile becomes a very weird shape. Okay, so as you can see, if let's say it's going this way, right? It doesn't make sense because there is a frictional force over here trying to resist the flow. So therefore, in the end, you actually cause turbulence around, and then you actually retard the whole flow. Okay, so you retard the whole flow. Therefore, as you can see, if I sub in 1 over here, okay, this is when I sub in +1, right? So if I have +1 over here, my whole flow rate is going to go decrease. Okay, gonna go in a negative way lah. Okay, flow rate is gonna go, in a negative way. So it's gonna be very turbulent and maybe in this direction. I don't know lah. Okay, so I'll leave you to find out. Okay, so when positive, okay, so remember, so when your pressure gradient is positive, it is always not in your favorable. If it's negative, then it is your favorable. Okay, so please, so be careful that what is the positive and negative. If the gradient is negative, your velocity profile will be positive. Okay, so it's a little confusing, but I hope you can understand. I just hope you can sink it into your brain. And then if it's so, as you can see the trend, similarly if your pressure gradient is gonna be higher, okay, number will be steeper. Okay, the values, okay, we're talking about the values lah. If your value is gonna be steeper, you're gonna go in this direction. Okay, so this applies to the whole cylinder. Okay, because as I say earlier, this thing, the pipe is based on the magnitude of R and the angle, right? The angle, how much angle is based on that. Okay, so definitely it's using, is only using this formula. Okay, so you may wonder why is it this one equals to this one. So I say is no. Okay, no, because it's different thing. Okay, it's different thing. Okay, although they take the same shape, however, um, it's like if you were to look in this point of view, okay, it's gonna be in this direction for this case. Okay, it's gonna go in this direction. So it's like let's say you have an umbrella, right? So this is the tip, and then it's going in this direction. So this is the handle, lah. Okay, example, lah. Okay, so if you have this turbulent one, which is when your pressure gradient is positive, okay, you have a opposite, because it's gonna I think I'm gonna confuse you. So let's just drop this. So just let you know that it's only in terms of this thing only. Okay, so I'm only been talking about this thing. And if you circulate 360 degrees, you're gonna cover around this portion over here. For this case, okay, for this case, if you were to circulate around, you're gonna get this cone shape, right? So this is what I mean, okay. So therefore, although it takes the same curve, but when you revolution, things gonna be a little different. Okay, it's a little abstract. So so if it's -1, so this thing over here is actually the same phenomenon of here. But however, if it's -1 only, okay, if it's -1, the velocity is normal. Okay, it's gonna flow in a normal range based on this one and this one only. So the pressure gradient does not affect the whole equation. So your velocity profile will be the normal one. If there is a pressure gradient, then your flow may increase. Okay, if this value, if your pressure gradient drops, your whole velocity going to increase. Makes sense, right? So therefore, if this is -1 also for your flow rate, okay, if you, because it's negative, so -1 times negative is going to be positive, so positive only this value. So this is always the constant, and then it's normal flow, and it just go forward, lah. However, if you have as I said earlier, if you have a change in the pressure, you can actually change the whole thing. You can actually increase the amount of flow rate. So this is like a multiplier. So if your pressure gradient is a key factor in your system, then you're gonna be careful that it may actually increase your flow rate or what. So if the pressure gradient is 1, okay, you are chillax, lah. So I hope I give you a very good introduction on the answer of this one. Discuss how the results of U and Q are affected by the pressure gradient. Okay, so next video I'll talk about the shear stress and the calculations. So I'll see you in the next video.